In today's lesson, you will be learning how to describe domain and range. We'll be looking at graphical as well as algebraic representations of functions. In this first graph, we have a linear function, but notice that the ends do not go on forever. We do not have arrows. On the left side here, we have an open circle, which remember means that we do not include this point. And on the right side, we have a closed circle, which means we do. So if we think about domain, this function will have an x value for every value all the way up to -5, but not including the -5. It will also have an x value for every value up to 4, but it will include the 4. So let's write that. When we write domain and range, we always want to start with the smallest number and go bigger. So we'll start with -5. Since we aren't including that, we use a parentheses. We'll go all the way up to +4. Since we do include that in the domain, we use a bracket. Now let's consider our range. Our range goes from -2, it looks like here, but we do not include the -2 because of the open circle, and it goes all the way up to 3 up here on the top, and we do include that because of the closed circle. So when we write range, we'll start with a parentheses, -2, since we do not include the -2, and we will go all the way up to 3, but we do include the 3, therefore we have a bracket. For this bottom one, give this a try. Stop the video, see if you can identify the domain and range, and then hit play. Our domain in this one, you should have recognized, goes from -1 to +1, but due to the open circles, those numbers are not included. So parentheses, -1, +1, and parentheses. If we consider our range, we are starting here at 0. Our function doesn't go any lower than 0, but we do have a point here at 0, so we would include the 0 with a bracket. It goes all the way up to +1, but due to the open circles, we would not include it and therefore have a parentheses. So remember what this means. We have x values anywhere from -1 to +1. For example, I've listed -1/2 here. If I go to where x equals -1/2, I can find that I have a y value. Range is the same way. If I choose a y value, say I choose a 1/2 here for y, I can go out and find an x value here on this side as well as on the other side here. Let's look at a couple more graphs. In this one here, notice that our left side has an arrow, so that means it goes up and to the left forever. So how will we write this domain? Well, if it's going to the left forever, that means it's going out towards -infinity. And remember, we always start from the negative and work to our positive. Our function goes to the right all the way to 4. And it looks like our circle here is open, so we would use a parentheses. Looking at the range, the lowest this function goes is down to -3. And it does actually hit -3, so we'll have a bracket here at -3. It goes up, but it goes up past 2 because our left side continues to go up forever. So that's going to go up to +infinity. Finally, here's our last one. Definitely pause the video and see if you can figure this one out. It's a little bit tricky. Okay, let's think about our domain. So let's look at the left side. This function here is going left forever. So I'm going to write -infinity because I know it will be out here at -infinity. But look what happens. As I move to the right, my function curves and it gets very close to this vertical asymptote where x equals -2. But it's never going to hit this asymptote if you remember your rational functions. It'll get very, very close but never get there. So as far as this leg is concerned, it's going to get close to -2 but never get there. So we would have another parentheses. Now let's jump to the other side of the -2. Well, here's our other leg, again getting very close to the -2 but never actually reaching it. So we will include a second set of interval notation for this leg. And we'll start at -2, but notice the parentheses because it's not ever going to hit -2. Now then it goes to the right, all the way out to positive infinity. All right, how about the range? Well, the range is going to be the same way. We'll look down here in the negatives, and this leg is going to go down forever into negative infinity. So we'll start with negative infinity. As we work our way up, this leg seems to be hindered again by an asymptote. This time we have a horizontal asymptote here where y equals 0. So this leg's going to get really close to 0, but not actually ever reach it. So we'll make a parentheses. Now let's examine the other leg. Same thing, really close to 0, but not actually reach it. And then it moves up and it continues forever out to positive infinity. This one was a little more complicated to write domain and range, but you can see that if you follow a pattern and you always go from negative to positive, from smallest to greatest, just take it one step at a time and you will be successful. Let's look at some algebraic representations. How do we determine domain in an algebraic representation of a function? Well, think about what domain is. Domain is every x value that works, every x value or every input that you can plug in that will give you an output. Well, what happens here in this function here, this rational function? We have a fraction. Can we put every value in here for x and will it work? Well, what can we not divide by? We can't divide by 0. So x cannot equal 0. So in this case, every single number will work except 0. So if we're going to write it in interval notation, we can go from negative infinity all the way to 0, but we can't include 0. We can jump to the other side of 0, just like you saw here, only with negative 2, and we can start the next leg and go from 0 to positive infinity. And there we have interval notation showing that every value of x will work except for the 0. What about this next one? How can we determine domain here? Well, again, we don't care about the numerator. That can be any number. But our denominator still cannot equal 0. So we have to ask ourselves, what will cause this denominator to equal 0? It's not quite as simple as this top one. Well, in order to do that, we can solve for x. To solve for x, we would add 9 to both sides. And then we are left with x squared equals 9. If we take the square root of both sides, we can solve for x. Remember that when we are solving for a variable and we have a radical, we can take the positive or the negative of the square root of 9, and that will give us the answer. So in this case, both a positive 3 and a negative 3 will cause us to have division by 0. Try it out. Negative 3 times negative 3 is positive 9, and 9 minus 9 is 0. Obviously, the positive 3 will give us the same result. How do we write this? Same way. Again, start from the smallest number possible, which would be negative infinity. We'll go all the way up to negative 3, but we can't include the negative 3. We'll go to the other side of the negative 3 and continue on, all the way up to positive 3, but again, we don't want to include the positive 3. So now we'll jump to the other side of it and go all the way up to infinity. Wow, that's a lot of intervals here. So let's see, how does this look graphically? Here's the graph of the function 2x over x squared minus 9. And you'll notice here at negative 3, we have an asymptote, and at positive 3 as well. So when we're thinking about our domain, this function has an x value all the way up to negative 3, but won't include the negative 3. We can jump to this leg, and again, on the other side of negative 3, we continue on all the way to positive 3, but not include it. Jump to the other side of the positive 3, and we have this leg, which starts at positive 3, but doesn't include it, and then continues to infinity. Now, you're not asked to do range for these problems, but if we thought about the range, we have to look at all 3 legs. This middle leg goes from negative infinity down here all the way through smoothly, no breaks, to positive infinity. That would be our range. Even though you can see the end behavior of these 2 outside legs follow a horizontal asymptote, it looks like at y equals 0. Let's look at our final problem here on this page. What do we have here? We have a quadratic, and remember that a quadratic makes a U. So how about our domain? Is our domain impacted? Is there any number that cannot be in our equation? Well, if we look at it, we're not having division by 0, and if you think about the end behaviors, this n to the left will go up and out forever, and the one to the right will also go up and out forever. So in this case, we have no restrictions on our domain. We go from negative infinity to positive infinity, or we can write it as all real numbers. Our range would be a different story if in fact we had to calculate our range. We would need to know this vertex to determine our lowest point. Let's try 2 more problems before we finish. Here we have a different type of function. We have a radical function. So how do we figure this out? Well, what cannot be inside this radical and give us a real solution for our domain? Remember, we can't take the square root of a negative number and get a real value. We can get an imaginary value or a complex number, but we cannot get a real value. So we know that this part inside, this x plus 5, will have to be greater than or equal to 0. We can have a 0 in here. We can take the square root of 0. We just can't take the square root of a negative number. So this one is very simple because we have 1x. We can just subtract 5 from both sides, and we know that our domain, written in algebraic notation, will be all numbers that are greater than or equal to negative 5. Let's write that in interval notation. How would we do that? Well, since we can be equal to negative 5, we would have our bracket, and they're greater than, any number greater than, so we would go to infinity. Let's look at this last problem. This one is a little bit more difficult. We have a quadratic inside our radical here, and we need it to be greater than or equal to 0, just like the top one. So how do we go about doing that? In order to do that, we need to solve our quadratic first. So we'll set it equal to 0, and we'll factor it in order to solve it. In order to factor it, we'll break apart the x squared, and then ask ourselves, what times what is negative 15? That adds to be negative 2. That would be negative 5 and positive 3. Solving each of these by setting them each equal to 0, we would end up with solutions of x equals 5 and x equals negative 3. So we've just found what 2 numbers make this whole quadratic equal to 0. But we don't know what our intervals are, so we need to figure this out. In order to do that, we'll need to draw kind of a number line. So I'm going to draw a line. So I've drawn my line and I've put my 2 values that cause my equation to be equal to 0. I can do filled in circles here because these are okay. If I plug these into my quadratic, I will have a value that is equal to 0. What I don't know is, do I want the interval to the left, in the middle, to the right, all of them, one of them? So what I need to do is I need to test some numbers. What I'm going to do then is I'm going to test, I'm going to pick a number. So I'm going to pick a negative 4. We'll try that one. I'll pick a 0. Any number in here is fine, and 0 is easy. And then I'll pick a 6. And now I just need to test those into my equation. So with this first one, negative 4 squared will give me 16, and a negative 2 times a negative 4 will give me positive 8 minus 15. Is that greater than or equal to 0? Well, 24 minus 15 is 9, and 9 is in fact greater than or equal to 0. So let's go ahead and shade the area that works. I just tried this negative 4 between negative 4 and 3, so I know that going this way, these numbers will all be solutions. Now let's go ahead and try 0. So if I plug that in, I get 0 minus 15 is greater than or equal to 0. And this is false. Negative 15 is not greater than or equal to 0. So this interval here between negative 3 and 5 does not work. That's false. Let's try the last one. Let's try the 6. 6 squared is 36 minus 12 minus 15. Is that greater than or equal to 0? 36 minus 12 is 24. And 24 minus 15 is also 9, coincidentally, and that does work because it's greater than or equal to 0. So I'm going to shade this area. So graphically, I have created my domain. But let's write this in interval notation. In interval notation, I would say that I would go from negative infinity all the way to negative 3 and include that value, and then I would start at positive 5 and go all the way to positive infinity. How could we write this using algebraic notation? Well, I can say that x has to be greater than or equal to negative 3, or x has to be greater than, oops, sorry, this first one is wrong, has to be less than or equal to negative 3, or x has to be greater than or equal to 5. So now I've shown my domain with all three methods here. And that concludes our lesson on describing domains and ranges.